Hello, welcome back to this series of lectures on numerical optimization. In the last class, we started looking at the convergence of Newton method, the order 2 convergence of Newton method. So, let us continue with that proof. So, in the last class, we showed that if the distance between xk plus 1 and x star is equal to half of mod of g 2 dash x bar k by g dash x k into x k minus x star square. And suppose if you are able to get some alpha 1 and alpha 2, which both are positive, such that the numerator here is less than alpha 1 for all x bar k, and the denominator here is greater than alpha 2 for all x k sufficiently close to x star, then we can write that mod of x k plus 1 minus x star is less than or equal to alpha 1 by 2 alpha 2 x k minus x star square. Now, if the sequence x k converges to x star, then we can clearly see that this is order 2 convergence. Now, let us see how to show that x k does converge to x star. Now, if you look at x k plus 1 minus x star, mod of x k plus 1 minus x star, and that is less than or equal to this quantity can be split into two parts. The one part is alpha 1 by 2 alpha 2 into mod of x k minus x star, and the other quantity is x k minus x star. Now, in order that the distance of x k plus 1 from x star is less than the distance of x k from x star, what we want is that we want this quantity to be less than 1. So, in other words, if this is this quantity is less than 1, then we can say that mod of x k plus 1 minus x star is less than mod of x k minus x star. So, that means that the new point is more close to x star than the current point x k, and if this happens for every k, then certainly we would converge to x star. Now, the question is that how do we choose that alpha 1 and alpha 2 which we mentioned earlier. Now, at x star we know that the gradient or the derivative of the function vanishes, and then the second order derivative of the function is greater than 0. So, since we know that if in fact we have chosen f to be thrice differentiable, so the derivative the second derivative of the function f is certainly continuous, and therefore, there exists some eta which is greater than 0, such that g dash x is greater than 0 for all x in the open interval x star minus eta to x star plus eta. That is because of the continuity of g dash, and we know that g dash x star is greater than 0. So, at least in the neighborhood of x star, the g dash has to be greater than 0. So, therefore, if we choose alpha 1 to be max of mod of g 2 dash x, where x lies in the interval x star minus eta to x star plus eta, and alpha 2 to be mean of g dash x, where x is again in the same interval, then what we have is we have mod of half into g 2 dash x bar k by g dash x k less than or equal to alpha 1 by 2 alpha 2 for all x bar k in that interval and x k in the same interval. So, let us call this quantity as beta. Now, so therefore, it is important for us to choose x naught to be in the interval x star minus eta to x star plus eta. Then we can show that this holds, and since this holds, this inequality holds, then if x naught is chosen properly, then we have this quantity which is less than 1, and then the sequence which the sequence in which x k plus 1 minus x star, the mod of that quantity is less than mod of x k minus x star for all k. Now, we also want the alpha 1 by 2 alpha 2 into x k minus x star to be less than 1. So, which means that the x k minus x star should be less than 1 over beta for all k, or in other words x k should belong to the interval x star minus 1 by beta to x star plus 1 by beta. So, therefore, we have to choose x naught such that the x naught is in the intersection of x star minus eta to x star plus eta and x star minus 1 by beta to x star plus 1 by beta. And now, if we choose x naught like this, the question is that does x k converge to x star or not. Okay, so now let us look at this expression that we had. Mod of x k minus x star is less than or equal to beta into x k minus 1 minus x star square. Now, the same quantity can be written. So, x k minus 1 x star can be written in terms of x k 2 minus x star and so on and so forth. So, finally, x 1 minus x star can be written as less than or equal to beta into x 0 minus x star square. So, if we combine all those expressions and write x k minus x star in terms of x 0 minus x star, then this is what we will get. So, so we have multiplied throughout by beta and we get this quantity. Now, this x k minus x star square is less than or equal to 1 over beta into this quantity. And this quantity, since we have seen that beta x k minus x star is less than 1 for all k. So, we also know that beta x 0 into mod of x 0 minus x star is also less than 1. So, this quantity is less than 1. So, therefore, mod x k minus x star is less than or equal to 1 over beta into a very small quantity as k increases, and that quantity will go to 0 as k increases. So, therefore, limit as k tends to infinity, x k minus x star mod of x k minus x star becomes 0. But you will notice that this is not a practical approach to choose x naught. For example, to choose x naught, we need the knowledge of x star. But nevertheless, this proof shows that if we start Newton method from some point x naught which is sufficiently close to x star, then it converges to x star with order of convergence 2. So, we have a theorem, let f be a real valued function and it thrice continuously differentiable. The thrice continuous differentiability is needed because we wanted the derivative to be Lifshitz continuous. So, that is why we need this, and let x star belong to R be such that g of x star is 0, the gradient vanishes and then the second derivative is greater than 0. Then provided x 0 is sufficiently close to x star, the sequence generated by classical Newton algorithm does converge to x star with order of convergence 2. So, this result can be extended to a general case where we have a function f from R n to R. But the important part is that the Newton method, when it starts with a point which is sufficiently close to x star, it does converge to x star with order of convergence 2. But the problem is that the initialization of x naught requires the knowledge of x star, and our aim is to minimize f x to get x star. So, this knowledge of x star is not there, and therefore, we cannot initialize x 0 properly, so that we can get global convergence of Newton method. In other words, the Newton method does depend a lot on x 0, a classical Newton method does depend a lot on x 0, and as this theorem says, the x 0 requires a knowledge of x star which is not available. So, but however, the important fact is that if we start sufficiently close to x star, we do get order 2 convergence. Now, let us look at some modifications of Newton method which are globally convergent. So, in other words, they do not require the knowledge of x star to get the initial point x 0. One can start from any point and converge to the local minimum. Okay. So, those methods are called modified Newton methods. So, we will see couple of those methods in this course, and let us look at the places where the modifications for the Newton method are required. Now, given xk and the direction Newton direction at the point xk, which is nothing but negative of the Hessian inverse into gk. Now, there are two possibilities. One is that the Hessian matrix is not invertible or is close to singular. So, in that case this direction really does not make much sense. Secondly, the Hessian matrix is suppose negative definite. So, in that case this direction is not a descent direction. So, if either Hessian matrix is negative definite or Hessian matrix is close to singular. Now, how do we modify Newton method so that this expression is positive? The quantity in the parenthesis is a positive definite matrix. Now, suppose if we fix some constant delta which is greater than 0 and find the smallest zeta k which is also greater than or equal to 0, such that the smallest eigenvalue of the matrix hk plus zeta ki is greater than delta. Now, by ensuring that the smallest eigenvalue of this matrix is greater than delta, which is a positive constant, we are ensuring that hk plus zeta ki is certainly a positive definite matrix. So, once we find the zeta k for a given hk, then we can choose a direction to be minus of the new direction can be chosen as minus of hk plus zeta ki inverse gk, and that is going to be a descent direction because hk plus zeta ki is a positive definite matrix. So, this is one modification that one can use. Now, secondly, if you recall that the classical Newton method does not use line search, or in other words it uses alpha k to be 1. Now, instead of that we can if we are given xk and dk, which is nothing but minus hk plus zeta ki inverse gk, what we can do is that we can use line search techniques to determine alpha k, and then xk plus 1 is determined as xk plus 1 is equal to xk plus alpha k dk. So, the two problems which were associated with classical Newton algorithm, one was that the Hessian matrix at xk is not necessarily positive definite. So, that problem is taken care of by ensuring that we add some zeta k I matrix or a constant times identity matrix to hk, so that the smallest eigenvalue of this matrix is greater than delta, where delta is a positive constant. So, once we ensure that and choose this direction as our new direction for search, then we certainly get a descent direction. Now, after having obtained a descent direction, the next step is to get alpha k using line search and update xk to get xk plus 1. Now, if we ensure that this line search techniques satisfy Armijo-Goldstein or Armijo-Wolff condition, then we have all the necessary criteria for global convergence of an optimization algorithm, that every time the direction chosen is a descent direction, the function value decreases and there is a sufficient decrease in the objective function, then certainly the method is going to converge. Now, the question is that how do we get this zeta k? So, sometimes very simple techniques are used. Suppose we start with some reasonable value of zeta k and do the Cholesky factorization of hk plus zeta ki. Now, if that Cholesky factorization fails because hk plus zeta k I is not positive definite, what one can do is that increase zeta k or maybe double the value of zeta k and try the Cholesky factorization again. So, while the Cholesky factorization of hk plus zeta k I is not successful, keep increasing the value of zeta k till that becomes successful. Now, remember that this zeta k has a very important role to play here. Now, if zeta k is very large quantity, then that dominates this expression hk plus zeta k I, and the method behaves like a steepest descent method. So, the order 2 convergence of Newton method is lost, but if zeta k is small, then hk will be a dominant thing. So, typically when the quadratic approximation of the function is good, the zeta k value will be typically small, and the most dominant term here between the two is hk, and therefore, this direction will be close to the Newton direction. And if zeta k is large, very large, then the direction becomes close to a steepest descent direction. So, whenever the approximation of the quadratic approximation of a given function is good, you will see that zeta k becomes a small quantity, and therefore, we have a direction which is close to the Newton direction, and the convergence will be very fast, and that typically happens near the solution. So, initially wherever the initial point x0 is, this method, because of this the addition of extra extra term to the Hessian matrix, make sure that the steps are taken if in an appropriate way, so that the convergence is achieved. So, one can show that this method, this modified method is globally convergent. Now, let us look at the algorithm. So, as I mentioned that apart from the initialization of x naught and epsilon, what we need is a parameter delta, and that parameter delta is typically given by the domain expert, or it requires the domain knowledge to set that parameter. The iteration counter is set to 0. So, while the norm of the gradient is at the current point x k is greater than epsilon, we find the smallest zeta k such that the smallest eigenvalue of h k plus zeta k I is greater than delta. Now, once we do that, then the direction that is chosen is minus h k plus zeta k I inverse g k, and this direction is certainly a descent direction, because h k plus zeta k I is a positive definite matrix. And then we use the line search, so that the function value decreases along the direction dk, and alpha k satisfies the Armyhoff-Wolff or Armyhoff-Goldstein conditions. So, compare now this with the classical Newton algorithm that we have seen. So, this step was not there in the classical Newton algorithm. Here in the classical Newton algorithm, we use dk is equal to minus hk inverse gk. Then the step length determination procedure was not there in the classical Newton algorithm, because we chose alpha k to be 1 in the classical Newton algorithm. And the rest of the steps are similar to the ones that we had earlier, that x k plus 1 is nothing but x k plus alpha k dk, and then k is equal to k a plus 1, that is the iteration counter is increased, and the whole procedure is repeated till a norm of the gradient at the current point x k is less than or equal to epsilon, and then we stop and we get a stationary point x k. So, we will not prove a result related to this modified Newton algorithm, but this modified Newton algorithm, it does have global convergence properties and has order of convergence equal to 2. So, the important thing that one should keep in mind is that the initial point x naught, there are no restrictions on the initial point x naught. So, unlike classical Newton algorithm, where which is very sensitive to x naught, this modified Newton algorithm is not sensitive to x naught. Now, we will look at some other modification of Newton method also. So, let us recall that we are trying to minimize this problem, minimize f of x, and in Newton method we consider f to be twice continuously differentiable and bounded below. So, we continue to use this assumption that f is bounded below. Now, the Newton method uses quadratic approximation of a given function f at a given point. And x k plus 1 is the minimizer of this quadratic approximation. So, the quadratic approximation uses the first order derivative and the second order derivative information, and so this quadratic approximation is used at a current point x k, and x k plus 1 is found as a minimizer of this quantity. Now, the question that one would like to ask is that how good is this quadratic approximation at a given point, or in other words, what is the region of trust in which this approximation is reliable. Now, if the quadratic approximation is reliable, then we certainly would like to minimize this quantity and go to the next step x k plus 1. But if the region of trust is not reliable, or the quadratic approximation is not reliable in the region, then we would like to reduce the region of trust, or reduce the region in which we can approximate f by a quadratic function. So, such methods which use the region of trust of the quadratic approximation are called the trust region methods. Now, suppose delta k is a positive quantity which is given to us, then one can define the region of trust to be omega k, and omega k is defined as set of all points around x k which are at a distance at the most delta k from x k. So, this norm is typically a Euclidean norm. Now, let us look at an example. Suppose that we have the function contours like this, and suppose this is our current point, and suppose the quadratic approximation of the function like this. Now, if one wants to go to the minimum, we simply take a step like this, and that may not reduce the objective function, or even if at all it reduces, if we do the line search, the reduction in the objective function will be typically small. So, instead what one can do is that in such cases, remember that the minimum lies somewhere in this direction. So, in such cases what one can do is that one can construct a region of trust around x k. So, if this is x k, we can construct a region of trust around x k, and then minimize the quadratic approximation that we have got in this region of trust, and then go to the new point. Now, if it so happens that the region of trust is good, then if we go to the new point and if we find that the approximation is really good, then we can expand this region of trust. On the other hand, if we realize that when we move from x k to x k plus 1, the function value has actually increased, which we do not want, then one can shrink the region of trust. So, depending upon how good is the our quadratic approximation of the function at a given point, we can decide whether to expand this region of trust or reduce this region of trust. So, by adopting the size of this region of trust, one can move to a new point, and that will ensure that we are not going in a direction which is away from the local minimum. So, let us see how to do that. So, omega k is the region of trust that we have defined based on the value of delta k. Now, instead of directly minimizing the quadratic approximation of the function, which is f q x, what we do is that we minimize the quadratic approximation subject to the constraint that x belongs to omega k. Remember that this f q x is a quadratic approximation. So, the subscript q stands for the quadratic approximation and k stands for the kth iteration. So, that means that the quadratic approximation is defined at a point x k, and or it is defined around point x k. So, there is a slight change in notation here that I have used. Now, this quadratic constraint optimization problem is easy to solve, but now the question is that once we find x k plus 1, which is a solution of this problem, then how do we determine the new region of trust, which is omega k plus 1, or how do we determine delta k plus 1, because once we define delta k plus 1, that can easily determine what is omega k plus 1. So, in other words, what we are interested in is finding out how this delta k plus 1 is obtained, if we have knowledge of x k plus 1, which is the constraint minimizer of this optimization problem. Now, one can use the ratio of the actual reduction in f to the predicted reduction in f to find out delta k plus 1, and we will see how to do that. Now, here is a simple algorithm to determine delta k plus 1 and r k. Now, this r k we will define it now. So, given that delta k, x k and x k plus 1, so we initially started with x k and then solved this optimization problem to get x k plus 1. And that optimization problem used delta k. So, given the knowledge of x k, delta k and x k plus 1, how do we determine delta k plus 1? That is the question that we would like to ask. So, let us define the ratio r k to be the function value at x k minus function value at x k plus 1 divided by f q k x k minus f q k x k plus 1. So, f q k is the quadratic approximation of the function at a given x k, and f q k is the function that quadratic approximation's value at the point x k plus 1. So, the numerator denotes the actual decrease in the objective function and denominator denotes the predicted decrease in the objective function. Now, if the quadratic approximation is good, then this ratio is close to 1. And if the quadratic approximation at a current point x k is bad, this ratio will be close to 0. And there could be situations where there could be an increase in the function value at x k plus 1. So, that means that this ratio could be negative. So, there are different possibilities for r k. Now, if r k is less than 0.25, so these numbers which are mentioned here, the algorithm is not so much sensitive to these numbers. So, one can change appropriately. So, if the ratio is small, which means that the actual decrease by the predicted decrease is very close to or less than 0.25, then which means that the quadratic approximation is not good enough. Now, if the quadratic approximation is not good enough, that means that we have to shrink the region of trust, and that is done by typically setting delta k plus 1 to be the distance between the x k plus 1 minus x k by 4. So, all the numbers mentioned here are typical numbers, and if one wants, one can change it based on the application. So, the delta k plus 1 reduces, and hence the region of trust also reduces for the next iteration. That is because the current approximation is not good enough. On the other hand, if the current approximation is good and the step taken is equal to delta k. So, if you look at this figure, so if starting from x k, if we go to a point x k plus 1 and x k plus 1 lies on the boundary. So, that means that the distance between x k plus 1 and x k is nothing but delta k. So, in such a case, what one can do is increase the region of trust to 2 delta k. So, whatever was the previous region of trust or previous delta k, that is multiplied by 2, and if none of these two things happen, then you retain delta k plus 1 to be delta k, and the algorithm returns delta k plus 1 and r k. R k is this ratio and delta k plus 1 is the new delta value for the new region of trust. Now, how does the modified Newton algorithm, which is based on trust region method, look like? So, as usual, we initialize x 0 and epsilon, and also initialize delta 0. So, this is a parameter that we will need, and the iteration count is set to 0. Now, while the norm of the gradient is greater than epsilon, we find x k plus 1 to be argmin x belongs to omega k f q k x. So, we minimize this quadratic approximation of f at x k subject to the constraint that x belongs to the set omega k. Now, we have x k plus 1 and delta k. Now, we are in a position to use our previous algorithm to determine delta k plus 1. So, that delta k plus 1 and r k are determined using the previous algorithm. Now, if we realize that the r k is less than 0, that means actually there is a increase in the function value from x k to x k plus 1. Then what we do is that x k plus 1 is set equal to x k. So, that means that the new point is same as the current point. So, we do not move to the new point. So, the change which was made here, that will be undone by this statement x k plus 1 is equal to x k. And remember that if r k is less than 0.25, we had shrunk the region of trust. So, that anyway will hold here, and therefore, will be since the initial region of trust was not good, we again use the reduced region of trust if r k is less than 0, and see how to move from x k to a new point. And then the rest of the procedure is x k equal to k plus 1, the iteration counter is increased, and the process is repeated till norm of g k is less than or equal to epsilon. And as output, what we get is a stationary point. So, in other words, if this is our x k and this is the region of trust that we have, and the corresponding radius is delta k. Now, at this, suppose the algorithm takes a step to new point x k plus 1, and if at this point we realize that the function value has increased. So, that means that this region of trust was really not good. So, we reduce the region of trust to a new quantity. So, this is the case where R k is less than 0. So, the new region of trust is defined, and then we again, so x k plus 1 is same as x k plus 1 x k. So, instead of taking this step where the function value actually increased, what we do is we come back to x k, reduce the region of trust, and then this is our new point x k plus 1, and then we try to use try to solve the problem, minimize f k q x subject to x belongs to now. So, let me call this as delta k nu, and so the corresponding omega k nu. So, that way we make sure that the function value does decrease at the end of every iteration. So, this method is called trust region method. So, both these methods, the earlier method that we saw and this method, they still use the Newton method ideas, but the way the steps are taken is not like classical Newton method. So, in the previous method that we saw, it was made sure that the Hessian matrix or the direction dk that we get is a descent direction, which is unlike Newton method, where the direction is always, in the classical Newton method, the direction is always minus h k inverse g k, and which need not be a descent direction. The second approach that we saw here, the trust region based approach, that makes sure that the maximum step is taken if the approximation is good, otherwise or in other words, the region of trust is large, otherwise the region of trust is shrunk, so that we do not overstep. Now, let us look at some modifications of Newton methods. Now, remember that in the Newton method, we have the direction dk to be minus h k inverse g k, and this requires, so this is Newton direction. Now, this requires the Hessian matrix and its inverse. Now, that is many a times computationally expensive operation, especially when the size of h k is very, very large. So, a set of methods were suggested, and what they do is that they approximate this Hessian inverse by a matrix, and then choose the direction dk to be minus bk gk. Now, if bk is a positive definite matrix, then we know that this is a descent direction. The direction dk is a descent direction. Now, how good is this approximation? That is the question that we would like to answer. So, in some cases it turns out that especially for quadratic functions, if this BK matrix is obtained in such a careful way, then this BK after certain number of iterations approximates the inverse of the Hessian. That is a typical of a quadratic function, but may not always hold. But nevertheless, this approximation is this approximation of Newton method or modification of Newton method is very popular, because if you look at this operation, this does not require inversion of a matrix. So, the computational effort required by this method to find a direction is much less, or is much less compared to the computational effort required by the Newton direction. Typically, if we want to invert a n by n matrix, the complexity of the operation is order n cube, and that is avoided in this case, because to get the new direction dk, we just need a matrix vector multiplication, and that needs order n square effort. So, the computational effort is saved in this method. So, such methods are called quasi-Newton methods, and let us now study some of those methods. Now, consider the problem to minimize f of x, where f is a function from Rn to R, and more importantly f is a continuously differentiable function. Now, if we use Newton method, we have to assume that f belongs to C2, and then as we saw earlier that Newton method depends on a quadratic approximation of the function at a given point xk. So, this is the quadratic approximation which requires the first derivative and the second derivative information, and the Newton direction chosen is minus hk inverse gk. But now, suppose we want to work in this setup where we want to minimize f(x), where f is a continuously differentiable function. That means, we do not want to use the second order information for this purpose. Now, given f which is a continuously differentiable, suppose we form a quadratic model of f at x, let us denote it by y. So, ykx, so this k stands for the quadratic approximation of f at xk. So, using Taylor series, if you write f of xk plus gk transpose x minus xk plus half x minus xk transpose, now instead of the Hessian matrix, because the functions are only continuously differentiable, so the second order information is not available. So, we write some matrix Bk inverse into x minus xk, where Bk is a symmetric and positive definite matrix. So, we have to make sure that this matrix Bk, whatever we have, is a symmetric matrix. This is like the Hessian matrix, which is also symmetric and also positive definite. Now, the Hessian matrix is not always positive definite. That is what we saw earlier when we studied Newton method, and in fact, that was one of the drawbacks of Newton method, that every time the Hessian matrix is not positive definite. So, if we make sure that this matrix Bk is positive definite, then one can choose a direction dk to be minus Bk gk, and that direction is called the quasi-Newton direction. Now, let us see how to use this quasi-Newton direction in our approach. So, the quasi-Newton methods use the quadratic model of f around xk using the matrix Bk inverse rather than the matrix Hk. Now, as I said earlier that this Bk inverse is either Hk, ideally we would like it to be Hk or its approximation. So, the question is that if we use the the direction dk to be minus bk gk, which is the quasi-neutron direction, and I get xk plus 1 to be xk plus alpha k dk, which is nothing but xk minus alpha k bk gk. So, how good is the approximation of bk inverse with respect to hk? And the second question is that once we move to the point xk plus 1, how do we get bk plus 1? How to update bk using the information xk plus 1, gk plus 1 and bk to get a symmetric positive definite matrix bk plus 1. So, this is an important question that we would like to answer, and whenever we update bk to bk plus 1, how good is that approximation to the corresponding hk plus 1 inverse? And when we do this update, are there any conditions that bk plus 1 should satisfy? So, these are some of the questions that we would like to answer. So, let us take a given point xk plus 1 and construct a quadratic approximation of f at xk plus 1, and that quadratic approximation will be denoted by yk plus 1. So, this k plus 1 stands for the fact that the quadratic approximation is obtained around xk plus 1. So, this function would look like f of xk plus 1 plus gk plus 1 transpose x minus xk plus 1 plus half x minus xk plus 1 transpose bk plus 1 inverse x minus xk plus 1. Now, how good is this quadratic approximation? Now, for this quadratic approximation to be good, what we want is that the gradient of this function at xk plus 1 should be the gradient of the function f at xk plus 1, and gradient of this function at xk should be equal to the gradient of the function at xk. So, at the two consecutive points xk and xk plus 1, the gradients of the actual function f and the gradient of the function y, they should match with each other. So, in other words, what we want is that gradient of yk plus gradient of yk plus 1 evaluated at xk should be equal to gradient of xk, and gradient yk plus 1 evaluated at xk plus 1 should be equal to gradient of f of xk plus 1. Now, you will see that the gradient of yk plus 1 is nothing but gk plus 1, which is the gradient of yk plus 1 evaluated at xk plus 1 is gk plus 1, and which is same as the gradient of f at xk plus 1. So, this equation is always satisfied. Now, what about the first equation? We want that equation also to hold, or in other words, the gradient of the function f at xk should be same as the gradient of yk plus 1 at xk. And so, we know that the gradient of f at xk is nothing but gk, and this gk should be equal to the gradient of yk plus 1 evaluated at xk. Now, if we evaluate this gradient, the gradient of this function at xk, what we get is gk plus 1 transpose into plus bk plus 1 inverse into xk minus xk plus 1. So, we want bk plus 1, or we want this quadratic approximation to be such that this condition is satisfied, or in other words, bk plus 1 should be such that bk plus 1 equal to bk plus 1 gamma k is equal to delta k, and the way this is obtained is that using this expression. So, since bk plus 1 is we want is a invertible matrix, so we can write gk plus 1 minus gk to be gamma k and xk plus 1 minus xk to be delta k, and write this quantity as bk plus 1 gamma k equal to delta k. So, this we want bk plus 1 to satisfy this condition, and this condition is called quasi-Newton condition. So, now let us look at this quasi-Newton condition Bk plus 1 gamma k equal to delta k. Now, certainly Bk plus 1 we want it to be positive definite. Now, gamma k transpose Bk plus 1 gamma k is nothing but gamma k transpose delta k, and that is greater than 0 for all gamma k not equal to 0 if we use Wolff conditions for line search, or in other words, suppose if you take Wolff conditions for line search. So, what we get is Gk plus 1 transpose dk is greater than or equal to C2 Gk transpose dk, where C2 is a positive fraction. In fact, C2 should be in the interval C1 to 1, but here I have intentionally mentioned it to be 0 to 1 just to indicate that it is a positive fraction. And so, if you take the right hand side to the left side, so what we get is Gk plus 1 minus C2 Gk into whole transpose dk is greater than or equal to 0, or in other words, so what we get from this is that gamma k transpose delta k which is greater than 0. So, if we make sure that Wolff conditions for line search are satisfied, then we ensure that gamma k transpose delta k is greater than 0, and gamma k transpose delta k greater than 0, it essentially means that the Bk plus 1 matrix will be positive definite matrix. Therefore, when Wolff condition is satisfied in a line search, there exists a Bk plus 1 which satisfies quasi-Newton condition. Now, how to get this Bk plus 1? Now, Bk plus 1 is a symmetric matrix. So, a symmetric matrix has of size n has n into n plus 1 by 2 independent variables. So, the number of variables here is n into n plus 1 by 2. Now, the number of equality constraints here or number of equalities here are n. And in addition to symmetricity, we also need positive definiteness of Bk plus 1. That is, all the principal minors of Bk plus 1 should be positive. So, that will result in n inequalities. So, in all we have n into n plus 1 by 2 variables, n equalities, and because of the positive definiteness, we want n inequalities to be satisfied. So, in other words, this is a problem in n plus 1 by 2 variables, which are to be found using n equations and n inequalities. So, you will see that the number of variables is much larger than the number of equations and inequalities. So, there exists many solutions which satisfy this quasi-Newton condition. Now, let us look at some simple ways of finding Bk plus 1. So, let us consider a simple way to update Bk, and let us assume that alpha is a scalar which is non-zero, and u is a n dimensional vector which is again non-zero, and let us update Bk to Bk plus 1 as Bk plus 1 is equal to Bk plus alpha uu transpose. Now, alpha is a scalar, uu transpose is a symmetric matrix of rank 1. So, that is why this is called the rank 1 correction. So, if Bk is a symmetric matrix, then certainly Bk plus alpha uu transpose is also a symmetric matrix, and therefore, Bk plus 1 will be a symmetric matrix. Now, if Bk is positive definite, is there a guarantee that Bk plus 1 is also positive definite? That is the question that we would like to answer. Now, before we do that, we want to find out what are possible values of alpha and u that could be used, so that quasi-Newton condition is satisfied by the matrix Bk plus 1, or in other words, what is that alpha and u such that Bk plus 1 gamma k is equal to delta k. So, we will choose alpha and u such that Bk plus 1 satisfies the quasi-Newton conditions, or in other words, Bk plus 1 gamma k equal to delta k implies Bk plus alpha uu transpose into gamma k equal to delta k. Now, how do we make sure that, or how do we get this alpha and u from this equation? So, as you will see that there are lots of possibilities to do this, and we will look at the simplest possibility. So, if we expand this and then equate u to be delta k minus Bk gamma k, then we can choose alpha equal to 1 over u transpose gamma k, or in other words alpha u transpose gamma k to be 1, and then that will satisfy this equality, and Bk in Bk plus 1 in this case will satisfy quasi-Newton condition. Now, will that Bk also Bk plus 1 also be positive definite, and how good is this rank 1 correction? We will discuss about those things in the next class. Thank you.